when is your homework 6 due? I don't even remember because I need to get you homework 7.
I think it's due next Monday, but I might be wrong.
I think it's Monday also, so I don't have to panic. I just don't like to leave you guys without homework on the go. Okay, it's 12:35. So I'll start. Yeah, so probably over the next 3 days, we'll be talking about metal-ion batteries with aqueous electrolytes. This just gives some indication of where some of the material in this lecture is coming from. This lecture is going to have Michael talk about the full open framework batteries, and Chong-In will talk about the high-energy aqueous lithium-ion batteries stuff. So I think probably I'll only be speaking for about 25 minutes, then Michael will take over, and then Chong-In will take over after that. So let's begin. So this is kind of an interesting story about this paper. I think it was the 1994 International Meeting on Lithium-Ion Batteries. And, you know, I had a talk there about something, and we had just finished this work in our group about rechargeable lithium batteries with aqueous electrolytes, and a patent had been filed a few weeks or something before the meeting. So it turned out that there was a hot topics section at the meeting where you could give like 4 or 5 overhead slides. There were no computers at the meeting, and I applied for one of these 5-minute talks and talked about this rechargeable lithium batteries with aqueous electrolytes, and it's sort of sounds like an oxymoron because everybody knows that lithium and water don't get along too well. But anyway, it was quite a huge hit at the meeting, and it's kind of neat how this all can work out. So it all turns out that you have to figure out where the common lithium-ion battery electrode materials, shown over here on the left, line up relative to the stability window of water. So water will evolve hydrogen if the potential is too low, and it will evolve oxygen if the potential is too high. So this is a chart that shows where the common lithium-ion battery materials lie relative to the water stability window for a 1 molar lithium plus solution, aqueous solution. It's also dependent on pH, so you can adjust the pH with counter ions. And when you look at this, you say, well, there are some materials that maybe we can make a water-based lithium-ion cell out of. And in our work in this early paper, we picked VO2B for the negative electrode and lithium manganese oxide spinel as the positive. So it's clear that if you work at very high pH, you'll have oxygen evolution problems with the positive electrode. And it's clear that if you work at acidic pH, you'll have problems with hydrogen evolution at the vanadium oxide electrode. So maybe somewhere around neutral pH, you can get something that works. That was the idea. So these are some data from that paper in Science, just showing charging and discharging of about a 1.5 volt system. 2 cells doing the same type of thing. And when you read this, it says that we used a 5 molar lithium nitrate electrolyte and then a little bit of lithium hydroxide to adjust the pH. So we wanted to use lithium nitrate as the electrolyte to get something close to neutral pH for the reasons I talked about on the previous slide. So these cells worked okay, and like most people promoting some new battery technology, you only show the first few cycles if everything becomes crappy afterwards. Oh yeah, and the reviewers objected to this work. They said, you know, how do you know it's lithium that's intercalating and not hydrogen? So this is what we did on the next slide. We made half cells with non-aqueous electrolytes, so in the typical lithium battery electrolytes. And then we took the 2 voltage curves from the half cells and took the difference between them and compared the difference between the non-aqueous half cells, which would be equivalent to a non-aqueous full cell, with the aqueous full cell. So down here it says the solid line is the aqueous cells, and the data points are calculated from these 2 half cells. So this convinced the reviewers that we actually were operating with lithium ions going back and forth between the electrodes. So like I say, the cycle life was lousy. And what are the issues with this? Well, one of the things you have to verify is that you're far away from these side reactions that you don't want. So for example, hydrogen evolution. So what happened here was we were doing cyclic voltammetry, and Meiji Zhang just ran the voltage down lower to see where hydrogen evolution would begin. So this gigantic current spike that you see happening at low voltage is the hydrogen evolution. So it turns out that at pH 9, which would be about here, there was quite a kinetic hindrance to the hydrogen evolution reaction, a big overvoltage associated with it, as you can see, maybe about 0.4 volts or so based on the scale here. And this is common for certain electrodes in aqueous solution. For example, if you think about it, the lead acid battery operates at 2 volts, and it should have no right to do so because the water stability window is only about 1.2 volts wide. And you'll learn later on from Chong Yin that you can extend the water stability window to be 3 volts and even greater. So it's kind of interesting that this sort of thing happens. So anyway, this sort of convinced us that we are far enough away from the hydrogen evolution reaction that the vanadium oxide electrode should be okay. Any questions about what I've talked about so far before I keep going?
Yeah, I have a question. Was there a reason why you guys chose 5 molar? And did you guys try other less or more concentrated electrolytes?
Oh man, I that's a long time ago. I don't remember. I would imagine that we must have tried other concentrations, and maybe the use of 5 molar turned out to be a premonition for what people learn later, is that when you make highly concentrated solutions, you can extend the water stability window. But we didn't recognize that at the time.
Okay.
And we were trying all kinds of stuff. You can see there's some boric acid thrown in here as well. Anyway, so one of the things that we did learn that happened was when we did cyclic voltammetry with this vanadium oxide electrode. If we operated at high pH, every time you did a cyclic voltammogram sweep, the signal would get smaller. And this meant that the material was dissolving in the electrolyte. And sure enough, if you analyzed the electrolyte afterwards, you found vanadium in solution. And as you lowered the pH, you would get more stability, but still, you could see the voltammogram still shrinking in terms of its height. And that means there's active material loss happening. And at pH 6.2, still shrinking over the first 8 cycles. So this is what I'm talking about. We did atomic absorption of the electrolytes and then back calculated the percentage of the vanadium oxide that dissolved as a function of the pH. So you can see that this is only 10 cycles, okay, 10 cycles only. So you can see that 10% of the vanadium oxide was dissolved even at almost neutral pH after these 10 cycles. So, this was a choice of electrode materials that could demonstrate that you could do this, but not a good choice for long-lived cell. So problems were hydrogen evolution, VO2B dissolution, and we stopped our work because of other priorities. So I haven't worked on aqueous lithium ion for 25 years. And everybody else was rushing to improve lithium ion. So it made more sense for us to do that.
Jeff?
But, yeah.
So you guys checked for vanadium dissolution. Did you guys ever check for manganese dissolution?
Again, I don't remember, to tell you the truth. I think manganese side was quite good. But from what I've been learning from talking to people doing aqueous zinc with manganese dioxide materials, the manganese dissolution is happening to some degree, even in cells with neutral pH.
Okay, thanks.
Yeah, so this is a paper, unfortunately the year isn't shown. It was relatively recent though. And what happened here was these guys decided to use lithium iron phosphate as the positive. And you can see that it's quite a bit lower than lithium manganese oxide spinel. And then they used lithium titanium phosphate as the negative side. So, when we did our work on the aqueous battery was 1994. No one knew about lithium iron phosphate until that it was useful until 1997, right? So nobody knew that LiFePO4 was going to be decent. And anyway, with these two choices, you can move to a pretty basic electrolyte. You can work relatively basic here if you want. So they showed some really quite incredible data. It's about a 1-volt cell, discharge and charge curves. And they showed it could operate up to high C rates, 10 C discharge, giving you about 80% of the capacity of the cell. And then they learned that it was important to get long cycle life to remove oxygen from the electrolyte. So even at basic conditions, pH 13 or pH 7, if you removed oxygen from the electrolyte, things worked really well. But if you had oxygen dissolved in the electrolyte, things did not work well at all. So this is another thing that we did not recognize when we were working on the system, lithium manganese oxide and vanadium oxide. We didn't realize the importance of oxygen in the electrolyte. So it would be kind of neat to go back to that old system and see what happened if you removed, you de-aerated the electrolyte before you started your cells. So this just shows that you can make a pretty good aqueous lithium ion cell with the right electrolytes and the right electrode materials. They're going to have fairly low voltage if you want to stay within the water stability window. Yeah, so then, things began to get interesting, and there were 2 really serious commercial efforts. Someone, I think, has a question. Maybe not. So there was Aqueon Energy, which was formed by Jay Whitaker. It was working on sodium-ion aqueous systems. They invested something like $150 million, raised a lot of money, built a production plant, and in the end, no one wanted what they could build because the energy density was so low. And then there's Natron Energy, which is doing really quite well. It's also a sodium-ion technology, which began as aqueous technology, but later on switched to non-aqueous. And Colin Wessels is the guy that runs this company. He's the CEO and brain, CTO, everything. And this is where Allison Keefe went to work, one of our students. So Michael's going to tell us the story about Natron because Michael's worked quite a lot on the electrode materials that Natron uses in his previous life. So I'm going to switch this over to Michael and he's going to take on. So I'm going to stop sharing, I think, and Michael will share.
Okay, yeah. Hey guys. Thanks, Jeff. Okay, so I'm sharing my screen and you guys can let me know when it comes up for you.
It looks good.
Okay, awesome. Yeah, so as Jeff introduced, this is really a quite cool type of battery that Natron Energy is trying to commercialize, and it uses a really interesting type of active material. And I want to introduce to you kind of how their battery works, and I think the goal would be really that we understand what their technology is all about. So if you guys have any questions as I go, of course, definitely interrupt. And I want to spend first a little bit of time on this slide, because I think it's really important that we understand their material well. So Natron Energy uses a type of battery material which is called a Prussian blue analog. So this is quite different from the materials that we talked about so far. The material that I sketched up here could be called copper hexocyanoferrate. So, and I think we should try to understand why it would be called like that. So you can already see that this is a cubic crystal structure, and we have copper atoms and iron atoms in this lattice, and kind of the framework that spans this cube is built up of these carbon nitrogen bonds. So, you know, the copper in this structure, as you can see if you look at it in detail, is always coordinated with a nitrogen, and the iron is always coordinated with a carbon atom. So that's why we would call this a copper iron hexacyanoferrate, because the CN group here that spans this framework is also called a cyano group. And we basically always have 6 of them surrounding the individual atoms. So if we look, for example, at this copper atom here on the right side of the cube, you can see, first of all, it's coordinated with the nitrogen. And you can imagine, you know, there's 1 here, 2, 3, 4, 5, and then there's the 6th one that we cannot see here. So the 6, of course, gives rise to this hexa number. And then cyanoferrate, because most of these materials use iron. And then copper is just an example that I chose here so that, you know, we have 2 distinct types of transition metals in this material. So, you know, the copper hexacyanoferrate material can easily be written as CuFe and then CN6 for the cyano groups. But if we want to write this in a very general way, we would write A for an intercalate alkali metal, and then M and M prime for the 2 different transition metals that are in the structure, and then the C and 6. And then we can have different stoichiometries here also. So the X would just mean, you know, that we have a certain stoichiometry in terms of the alkali metals that are intercalated. And then we can have different ratios of the 2 metals. So we can have the M prime Y, and the M2 prime would be there Z times in this stoichiometry. And then we have also so-called interstitial water. So, you know, these open sites in this framework are also called interstitial sites, and water can be present here from the synthesis. So, and the unit cell volume of this material would be, you know, 10 angstrom times 10 angstroms by 10 angstroms, so 1,000 angstroms. And here on the right side, I drew the ionic radius of sodium, because, you know, natron energy, so from the name you can already infer that they use sodium as the intercalant alkali metal. So you can see, you know, this is fairly small compared to these large interstitial sites that you have in this material. So the cool thing about these open framework batteries that use these Prussian blue analogs is they can, you know, readily intercalate different types of alkali metal ions. And as you do this, then you have to compensate for the charge that you put into the structure by reducing the oxidation state of the transition metals. So I want to show you the slide in Vesta, the structure of this material, because I think then it becomes a little more clear. But do you have any questions up to now?
Yeah. How does the stoichiometry work? Are the cyano groups tied to the number of M double prime metals, or are they tied to both the metal amounts?
So the M prime material here, this would be the metal that is coordinated with nitrogen, and the M2 prime is the metal that is coordinated with the carbon in the structure. So I want to say that the stoichiometry of these cyano groups would be tied to both the metals, but in fact it is true, and this is also in the case in Natron's materials, that you can have this Y and this Z not be perfectly equal to each other. So I'm not quite sure really what the structure then would look like, but it is true to have different amounts of the M and the M prime material. Maybe Jeff can comment on that if you have an idea about that.
No, I don't know.
Yeah.
Okay.
So we will see a few examples of this material, and then maybe it becomes more clear as we look at these versions that Natron Energy is using. Okay, so let me switch over to Vesta. I hope you can see now the crystal structure in Vesta.
Yes.
Okay, cool. So here, it's useful, I think, to rotate this and show you guys a little bit more how this is made up. So we already saw the way the material is built. So, the iron in red coordinated with the carbon, and in this case, copper coordinated with the nitrogen. And then we have these cyano groups spanning the cube, really, in this open framework. And then, as we, for example, rotate it this way, you can really see this large open structure, these interstitial sites that you can also actually probably see a little better if we make this space filling. So there's a lot of space really to put various intercalant ions of different sizes in this material. Okay. So now let's see what happens if we change the amount of sodium that is intercalated in this material. So now this version that is shown here, that is iron hexocyanoferrate. So it's basically purely made up of iron in the different sides of the lattice, and the hexocyanoferrate groups span the cubic structure. So this is only one type of transition metal here. And if this structure doesn't contain any sodium, then iron would be in the 3+ oxidation state. Now, as we sodiate this material, so we put the blue balls in there, which is sodium, some of the iron will go to its 2+ oxidation state to balance the charge that comes from the sodium. And then we can even sodiate this material more, and upon this it would change its structure slightly to a rhombohedral structure, where then these sodiums don't really sit exactly on top of each other anymore. That might be better, energetically. But you can see that now we have only these green dots, which is iron completely in the 2+ state. So, okay, we already know this is the general formula of this material. A, as I said, is the insertion species. In this case, it's sodium. Can be also potassium or other ions. And then the two M's denote the different transition metals. So in this case, it's iron in both cases, but it can also be iron or copper, or manganese, nickel, and others. And so in principle, both of these M sites can be redox active, just like in this case where we have iron in both cases. And we already mentioned these cyano bridges, these CN bonds that create this open cubic framework structure. And yeah, there can be interstitial, or also called zeolitic water in these materials. So, and really a big advantage of this structure is that, these large interstitial sites really allow a very rapid insertion and removal of ions, also in a zero strain fashion. If we would intercalate this material up to this stage, then we would get roughly 70 milliambars per grams for this 1 electron redox with sodium intercalation. And the other big advantage of these materials is you might say, okay, this is not a very large capacity compared to other materials that we study, but these materials are extremely cheap. So, you can buy them by the ton, and they would cost roughly $2 per kilogram for this version now of the Prussian blue analog. By the way, Aaron, this is a structure now that does not have equal amounts of the 2 irons in the structure. Well, I guess from this structure, we could infer that maybe, the amount of the cyano groups is bound to the amount of the transition metal that coordinates with the carbon. Well, maybe that's what it is. Yeah. But now, from this fairly cheap material, you can, back on the envelope, calculate cost per energy on a materials level. So, if we take the $2 per kilogram and we divide it by the energy that we can get out of this material, which would be, the 70 milliamp hours per gram or amp hours per kilogram from here. And then if we assume we had a cell that, has an average voltage of 1.6 volts, you multiply those two, you get the energy, then this would amount to roughly $18 per kilowatt hour. And this is where, these materials become attractive. I mean, of course, you would have to add extra cost for packaging and all of these things. This is really only on a materials level, but it is fairly cheap. And on top of that, you have advantages that I already mentioned, like very rapid intercalation and removal of ions. So let's look at what Natron, did with this material. So this is their first generation cell, and it's also described in the paper that Jeff mentioned initially. So this is a 1 volt cell, and it uses 2 different versions of these Prussian blues. So 2 different Prussian blue analogs on anode and cathode. And they are both coated on aluminum current collectors. And the electrolyte is sodium ion containing electrolyte, they say. And there's a separator, of course, also in there, which is not drawn here. So let's first look at the anode. So their anode is, well, maybe, so one of you wants to name this structure? You guys want to give it a try? This sodium MnMnCN6. So this would be called sodium manganese hexocyanomanganate. So it's not a ferrate anymore because it doesn't have the iron anymore, but here the manganese is what's coordinated to the carbon atoms in this open framework structure. So you can see here, we start off with manganese atoms on the corners of these little cubes. And the way Natron likes to write the structure is in this way, which is also quite useful. So we have manganese 2+ ions. That's these ions here, or atoms, which are coordinated to nitrogen. And then we have the CN bond, and the manganese, which is coordinated to the carbon, would be this one in our way of writing it. And in their cell, this one changes the oxidation state between 2+ and 3+ as we sodiate and desodiate this material. So as we remove the green balls. And on the cathode side, we basically have exactly the material that we discussed in the first slide. So copper hexocyanoferrate. So in this material, as we already said, we have copper, which is coordinated with the nitrogen. We have the hexocyanoferrate framework structure, and iron coordinated to the carbon. So that's this iron. And in the way that natron cycles the cell, iron is changing its oxidation state between 2+ and 3+ as we insert and remove sodium from the cell. So in a way, it's a symmetric cell, but it uses different types of Prussian blue analogs on anode and cathode. So the operating voltage is 1 volts, and we already mentioned manganese is doing the charge compensation on the anode side, iron is doing the charge compensation on the cathode side, and people like to write this with these Roman numerals sometimes. Is that kind of clear how this first generation cell works? Just let me know if you guys have any questions. So this is a little recap. Maybe we can just quickly read it. Okay, so this is from their paper. So the open framework structure of Prussian blue analogs is fundamentally different from other insertion electrode materials because of its large channels and large interstitial sites. This structure is composed of a face-centered cubic framework of transition metal cations, where each cation is octahedrally coordinated to hexocyanometallate groups. So for instance, the material that we discussed would be copper hexocyanoferrate. So a 6-fold carbon coordinated iron, right? Those were the red balls in our model, and then a 6-fold nitrogen coordinated copper. And we have these CN ligands that build up the cubic structure. So we have these large interstitial sites, they're also called A sites, within the structure that can accommodate zeolitic water, so this interstitial water, or hydrated alkali metal ions. So, and then the result is, a material with the general chemical formula. And now here comes another way of writing this general structure, which is a little cumbersome, but we can talk about it. So A is the intercalent alkali metal, and then they have PrCN6 times a certain amount of water molecules. So A is the alkali metal ions, such as potassium or sodium. P would be the first transition metal cation, such as copper, nickel, or can be iron. And RCN6 is the hexocyanometallate anion. So you can also interpret this as an anion if you look at the Fe and the CN6 as a whole. Can also be a manganese, chromium in the place of iron. So, and then both the P side transition metal cation and the RCN6 3- hexocyanometallate anion can be electrochemically active. We saw this, in the case where we had the FeFe on the second slide. And that's why they like to write this in this general form, where they have the cyano group in the middle, the CN bond, and then the P transition metal or the R transition metal. And the redox state of these metals is denoted in our case by these Roman numerals. You can also more generally write this as other letters. And these letters, they represent the valence state or oxidation state of the transition metals. So in the case of natron energy, it is sodium, manganese, CN6, or sodium, copper, iron, CN6. Okay.
I have a question here. Oh, sorry. Go ahead,
Okay.
Aaron.
You go ahead, Nico.
So I was wondering, so it seems like the water in the hydrate form is occupying the interstitial sites because there's these large holes. So does that impact diffusion? Because on a charge cycle, then we both have to remove the waters and also add in sodium ions? Or are these holes large enough that that's not an issue?
So definitely they take up interstitial sites. I would say these, the interstitial water molecules. I'm not sure though, if they would really, at least if they are only present to a certain extent, block any diffusion. I mean, you really have to think of this as a really nice open framework structure, where you can have 3D diffusion basically in all directions. So even if there is a water here and there, I don't think it would impact the diffusion much. That's kind of my take.
Right. Yeah, that makes a lot of sense. Thank you.
Yeah, so is it possible to do more than one sodium per material, I guess? Can you go like past more than a stoichiometry of 1?
So you can do that. That's, for example, drawn here. So if you fill this material all the way up with sodium, so every interstitial site is filled with sodium, then it would be sodium 2 FeCN6 in this case. So you can do that, but it goes along with a change of the crystal structure. And we will see actually at the very end that this is currently a challenge for these materials. Of course, it would be very nice because you get twice the capacity, but these materials don't cycle well anymore if you do that. In the same case, but I would say this is not very well understood yet. If you fill it up to this stage with divalent ions, you run into the same problem. To this middle stage, where
so
then
it
also
sounds like a charge, potentially a charge issue then.
So we recently did actually a study where we used this material. It was nickel hexocyanoferrate, and we wanted to intercalate this with sodium. Works beautifully, but if you add divalent ions like calcium, for example, to the structure, then you see a very rapid capacity fading. And yeah, I think it's a question probably of how far you take your charge compensation in the material, whether you want to bring all the ions, in this case, the iron atoms, to a 2+ oxidation state. I don't want to speculate too much as to why then, you have these structural problems with calcium, but you can imagine maybe 2+ ions, maybe there's some place exchange happening. So it's really, I think, not fully understood, but the material cycles very well if you go up to this sodiation state. If you go further, then you get into trouble.
Thanks.
Okay. So I think we can continue a little bit and talk about the 2nd generation cell, which is also really interesting now, I find, to compare kind of what they changed, because I mean, Natron Energy is obviously, still, a young company, I'd say, and they constantly improve their technology. So let's see what's happening in the 2nd generation cell. So here they say, maybe let's read their words down here. So it's a 1.6 volt cell now compared to the 1 volt cell that you guys saw before. with 2 different Prussian blue analogs. They say neither of the electrode limits the cycle life, and there is no net change in volume during cycling. The electrodes operate within the stability range of the electrolyte. And the really cool thing is, because of that, you don't form a passivating layer on the electrodes. So no SEI, no solid electrolyte interface is formed in their technology. So, in our case, in a lithium-ion battery, as we heard in the electrolytes class, the graphite is actually operating below the stability limit of the carbonate electrolytes, right? And luckily, we form this passivating SEI layer that prevents further electrolyte reduction. But in Natron's case, this is not even needed because you operate fully within the stability limit of the electrolyte. And that's, of course, better because, you don't have impedance built up in these cells from a passivating layer that's on the surface. And then they say no magic additives are in these cells. And the other really cool thing is you also don't need a formation step in their technology. So, we learned in the other classes that people typically do, a very slow cycle after assembly of the battery cell, where a lot of gases are generated, and you form, this passivating layer on the electrode, which is, of course, time consuming, and time is money. So it's really a nice fact that in their battery technology, you don't need a formation step. Okay, so let's look closer at their cells. So again, we have 2 aluminum current collectors and 2 different Prussian blue analogs coated on those. And then they put this together again in a sodium containing electrolyte with a separator. And now they get a 1.6 volt cell. So obviously they changed something to their electrodes. So here they only, draw these sketches of the crystal structure of the Prussian blue analogs. But let's look a little bit more closely as to what changed from generation 1 to generation 2 here. Okay, so this is first a slide that deals with the cathode. On the right side, you see an SEM image of this cathode. You have these large secondary agglomerates made up of really small primary particles. So, and what they use as the cathode now in this Gen 2 is a sodium manganese hexocyanoferrate material. So they swapped out the copper, which was here initially, for manganese. And we can try to understand why they did this. So, but first of all, these materials are made in an aqueous synthesis. You have a manganese 2+ precursor, a manganese 3+ precursor, and a hexocyanoferrate precursor. And typically people use co-precipitation. So you just mix these precursors together, and what precipitates out is, your active material in the desired crystal structure, if you do everything right. And we already mentioned, these are maybe 10 to 20 micrometer agglomerates, maybe 200 to 500 nanometers primary particulates that make up these agglomerates. And they say the structure of their cathode can be written like this. Okay, so let's look at this. So we have sodium, which is intercalated in the material from the start as we make it, because oftentimes they use, sodium-containing precursors here. So we have sodium intercalated to an X equals 1.3, and then for these metals, which were our M prime metals, the metals that are coordinated to the nitrogen site in these open frameworks, we have a mix. So it's now manganese 0.8 and iron 0.2. So manganese in the 2+ state, iron is in the 3+ state. And then we have the hexocyanoferrate group, which is iron in the 2+ state, and our CN6. And this material also contains some water in the interstitial sites. And now with this structure, we basically have a couple of reversible reactions that can happen. So you could imagine that this iron, which is coordinated to the nitrogen, can change its oxidation state between 3+ and 2+. You can also change the oxidation state of the iron that is coordinated with the carbon from its 2+ state to a 3+ state. Or another option for charge compensation in these materials is that the manganese that is now there instead of the copper can change its oxidation state between 2+ and 3+, and this manganese is also coordinated to nitrogen, same as this iron. And natron, though, doesn't make use of all these different redox couples that are available in the cell. They limit themselves to the Fe 2+, 3+ redox, and they use the Fe atom that is coordinated to the carbon. So now, why did they change from copper to manganese? I think that is pretty obvious if we look at the cost of those different materials. You know, I mean, these are very rough numbers, but copper is maybe around $10 per kilogram. Manganese you can buy by the ton, you know, for very cheap. So especially in these batteries, which are not, you know, extremely high performing in terms of their energy density, I think it is very important that the cost is low. That's really the selling point for these batteries. So that's why it's an advantage for them to go to manganese, especially if they not even use, you know, this redox, but only use the Fe 2+, 3+ redox.
Can I ask a question here?
Yeah, absolutely.
I think the manganese that's $4 a ton is a typo. It's definitely not $4 a ton. That's crazy.
Oh, is it maybe per kg?
$4 a
Okay.
kilo, yeah.
Okay, I can look this up for next time. Anyways, we're almost at the end, but yeah, that would be probably too cheap. I just did a super quick search. Probably I mistyped. But I mean, we can say manganese for sure is cheaper than copper, so it's good for them to use cheaper materials for this battery. Okay, so maybe let's just finish this slide. Before then, next time we can continue with the anode and what they changed there. But here they plot the potential of the cathode versus sodium metal. So it's the same what we do in lithium half cells, or you know, half cells of our different lithium-ion battery materials. And so now you can see that you have maybe, you know, not real plateaus, but you know, maybe 3 features that you can make out here. The high voltage capacities associated with the manganese 2+, 3+ redox. If you want to go to that higher voltage, then this capacity you get like at moderate voltages here is from the iron 2+, 3+. And then the iron that is coordinated with the nitrogen, if that undergoes a 2+, 3+ redox, then you get lower voltage capacity, let's say here. If you use all redox couple that are available in the material, you can extract, you know, 120 millibars per gram from this material. Only the iron hexocyanoferrate 2+, 3+ redox here in the middle would give you about 80 milliampere hours per gram. If you plot this as a differential capacity, dQ/dV versus the voltage, you can see these redox features more clearly, and you can see that this middle redox is associated with the iron 2+, 3+. So yeah, you guys can keep this in mind for next time. Maybe you guys wonder why they are only using the iron 2+, 3+ redox if they had the option, you know, to use also the other redox couples for more capacity. But I guess it would be a good time to stop and talk about the rest of the slides next time, if that works. And we could still have a few more questions if you guys want. Got a couple minutes.
So I have a question. Based on this so do they synthesize the composition that's sodium 1.3, right?
Correct. Yes.
So I guess, is that right around the 100 milliamp hour per gram mark, or is that a little bit past? I'm just trying to figure out if there's any irreversible capacity from that first charge where you might have too much sodium to begin with. I don't know if that's the case.
Could be, Aaron. So you know, for the iron material, which has no manganese, so it would be a little different in terms of the grams of material, just because of the weight of all the different metals. But for that material, if we had 1 sodium, it would be about 70 millibars per gram or so. So yeah, it could be that this is close to the 100 millibars per gram, but I don't really know exactly how much capacity you get out of this. It's a little unclear here how much, you know, what the stoichiometry would be if you, you know, go between 0 and 120 milliamp per gram here. One could work it out probably by, you know, with a piece of paper looking at the oxidation states of the different materials.
Yeah, I was just trying to figure out where you would start once you like put it into a cell, because it's sort of like not fully charged and not fully discharged.
Yeah, exactly. You know, that's a really good point, actually, and we should talk about this next time for sure, because it is a challenge in these materials to get the, let's say, starting SOC right, you know, because you basically make these materials either containing sodium or empty, deprived of sodium. So Natron Energy has a way to make them, you know, either way. And that's really nice, because if you have your synthesis really perfectly dialed in, then you can synthesize this material in a way, you know, that one electrode is containing all the sodium you want to cycle, the other one is empty and basically ready to accept the sodium. But of course, you can imagine if you are a little off, then it will be, and you can end up in a situation where you have only limited capacity in a certain voltage window.
Yeah.
So
okay. Thanks.
To get this right. Yeah.
Michael, I had a question that even if we are going to this sodium 1.3, the maximum amount of you know, cyclable sodium is limited to the amount of this Fe, which could be you know, ionized here. So is it still like 0.9 in this case?
Oh, can you repeat that? I think I didn't get it fully, Divya.
I mean, like the sodium here is 1.3, but the iron, which is paired with cyanide, so that is still 0.9.
This one, right down here, yeah.
Yeah, so is the amount of cyclable sodium in these batteries or in these materials, is it still 0.9? Because every time we add a sodium, we need an iron to, you know, go to another oxidation state. So
that would be the case if you only work with the Fe2+3+ redox couple that is associated with the iron that is coordinated with the carbon, you know, so with this one. But so in this case down here, where they cycle over the longer, over the larger voltage window, you know, surely as they indicate here, you have manganese and this other iron also participating in charge compensation. And then you're not limited to this 0.9 worth of sodium that you can pull in or out. Then you can have more.
yeah, that's true.
I guess you're right in the sense that if you only work with and you guys can comment if I may not get this right, if you only work with the Fe2 plus 3 plus redox couple here, which is present in a stoichiometry of 0.9, then you can also only remove or insert 0.9 worth of sodium, which is a monovalent ion. So, you know, as you put one in, you have to change the oxidation state of an iron from 2 plus to 3 plus, or from 3 plus to 2 plus rather. So in that case, you're right, yes. If, in my opinion, if you only have these irons that do the charge compensation. And that's why in that case you have a smaller capacity, you know, that you can cycle.
I wonder if the extra sodium is there for stability reasons, so that you don't totally empty the material.
Yeah. So this material, I think it is fairly stable, even if it's completely deprived of alkali metals. At least Colin told me that they make these materials completely empty too. So they synthesize these in the completely desodiated state as well. Now, I don't know, maybe they leave a little bit of sodium in there, but yeah. Yeah, it could be possible, Ron, that you might want to, you know, have a little bit more of sodium in there from the start, and then you cycle 0.9 sodium worth of material.
Michael, I had one more question. Is this water quantity here, is it like is it helpful in adding the strength to the material, the zeolitic water, or is it something unavoidable?
So I always thought about this rather as you know, a consequence of this material being synthesized in an aqueous synthesis, and then you end up with zeolitic water in the material. But if you could avoid it, I guess it would be better. I'm not quite sure if that would add any stability to the material, and to be honest, I don't know in which way it would do that. You know, you have many chemicals which contain this crystal water in their material, right? But I'm not sure if it would add anything to the stability.
Okay, I see. Thanks.
Michael, so the operating voltage of this cell, which is 1.6 volts, is that already go beyond the decomposition voltage of water? And I saw on the typical composition of the electrode, the water is here. So I guess this water wouldn't be able to release into the electrolyte, right? Because if it's released during the operation, it will be the 1.6 volts will be beyond the decomposition voltage of H2O.
Yeah, that's actually an interesting thought. Yeah, what happens to the water if you go beyond the stability limit of water? So one thing is for sure, you already kind of resolved the little puzzle here, you know, that how can they operate this at 1.6 volt cell voltage, right? We will look at the voltage profiles in more detail in the next class. But so this is, unless you have tricks like Zhang Yin has, very difficult to do in an aqueous environment. Definitely, you know, then water in your aqueous electrolyte could be oxidized or reduced at the electrodes. I'm not quite sure what would happen to the zeolitic water inside the crystal structure. I don't know if anyone else has an idea about that, but yeah.
Well, let me make a comment. I have an email from Colin that talks about the difficulty of this water that's unavoidable in the synthesis, in the subsequent operation of the cell with, I don't want to steal the secret, but with the electrolyte that's used for the Gen 2 cell. This water is creating trouble for them.
Okay.
They want to hire someone to help them with that.
Okay.
Either from the electrolyte side or from the solid side.
So you haven't
Yeah,
discussed the electrolyte here. That's acetonitrile, right? They're using.
You cheated.
Hmm?
You must have cheated and gone ahead in the PowerPoint.
No, I haven't. I've actually seen his presentation, so I've heard they mentioned acetonitrile before.
So anyways, you guys already had all the slides, right? Of course, in their Gen 2 cell, they don't use a aqueous-based cell anymore. They use an organic electrolyte. And I mean, as Jeff said, then probably, you know, residual water that you have anywhere in the cell could lead to problems, you know, because then you have side reactions. But yeah, this water that is initially in the material from the synthesis could be one such source of water, I guess.
Okay, this is great. So Michael, thank you so much for taking the lecture, and you'll finish next time, I'm sure.
Okay.
So that means Chong-In has to be standing by to sort of start midway or thereabouts on Wednesday.
Yeah, perfect. Sounds good. Thanks for all the questions, guys. And yeah, I appreciate the discussion.
Okay, bye everyone.
Bye.